we do in the class. I think it's for the benefit of the students. Again, as I said, even though it's the first time I teach it, and I don't like the idea of working on preparing the material as well as teaching it at the same time, but this is life. So, I'll have these posted on the class website. So the class website, as I said, is if you go to my the university, my link on the university website, you click on web page, it will go there, or you can just go to seeclab.com, and you can then go to teaching 325, and there will be a password. I think the password I used is 325 summer. 325 SU. I was gonna use hot summer, but then I decided not to. So the password is, I'll write it down. The password is 325 summer. Right. So please note that. And I will have everything posted up here. I mean, of course, I just put the skeleton up here and just started putting a few things, but it's not fully up and running yet. We'll run through the syllabus, and then we'll see how we'll get started with syllabus, logistics, and then we'll get started with the course. So any questions before we get started? Good.
They're going to be homeworks, right?
Yeah, so I will go through the syllabus, but homeworks will not be graded. So you will submit your homework, and I will see you will get a grade for submitting the homework. They will not be graded homeworks. You will have quizzes on the homeworks, either probably in the lab session or the recitation session. Probably in the recitation session, maybe a quick quiz on the homework. But no, we will not. Again, it's a textbook, right? 5 minutes. I bring the solution manual, right? But it's for your benefit to solve the problems, right? So the exams, I will not bring exams out of Mars. The exams will be out of your homeworks, your textbooks, questions, etc., right? So examples, homeworks, similar textbooks. There's lots of textbooks on electronics. Electronics is a very mature science, I would say, and there are lots of good textbooks on electronics. So there's a lot of problem sets that I can work with to create homeworks and stuff. But for me, I think again, your homework is something that you need to do. I mean, you will not be graded. You spend the time doing it, right? I mean, you will not be graded on it, good or bad. You submit it, you will get the points for the homework. I think that's fair. And then you take a quiz on that, so that the quiz and the homework quizzes will be one of the problems of the homework, but maybe with the numbers changed or something like that, right? So it's really okay. Did you do your homework yourself? That's really it. That's the homework, and you will get, I think, 5 points for submit. I think 5% of your grade is on just submitting the homeworks. Yeah. So we'll look at the syllabus and see what's. Okay. Okay, so as we all know, so this is a 4-hour course, and it will be an introduction to electronics. Basically, it's a continuation of what you did in your circuits course, right? But with a little bit more advanced knowledge and analysis that you will apply. So you really need to have a good background in circuits, and that's really something that's very vital here. 314, I think, is a core requisite for the course. It's not a requirement. I think I should say core requisite. Yeah. I'll modify that. So it's or registration therein, I guess, means that it's a core requisite. So we of course, again, we're developing electronics, or we're studying electronics, so we are able to understand and develop electronic systems. To do what? Mainly to process signals. Yeah. So and that's where the knowledge of 314 in parallel is an interesting topic to understand. I think in 314 they address things like quantization of signals and signal processing applied to signals. And again, if you do not understand that, then you cannot develop the electronics required to make that happen. Yeah. So that's why it's a prerequisite, not a prerequisite. Yeah. But 214 is definitely important, right? So understanding how to do Kirchhoff, applying Kirchhoff current law, Kirchhoff voltage law, nodal analysis, Thevenin, two-port networks, etc., etc. So I never taught 214 before, but so it seems that because based on the syllabus here, it seems that in 214 we do not cover op-amps, right? We do. There's a good, decent coverage of simple coverage of op-amps. Similar? Is it similar to 215 you said, or similar? Okay. Well, because I never taught 214, so I taught 215 the last time, first time this last semester, but. So it's you have an idea of op-amps, so it's good, yeah. So we do cover that in a much more depth in this course, even though I would say a lot of the beginning material for the op-amp material is something you've studied before, so it will be a review, I would say, in that case. So we will start off by sort of looking at understanding what a signal is and applying simple analysis to equivalent circuits similar to what you've seen before in 214 to understand how circuits operate and how they amplify signals, etc., etc. Just from a lumped parameter analysis perspective, and that's sort of what we will start with in chapter 1. And then we will, there's chapter 1 that has some section on semiconductors. We will sort of move that to when we study diodes in chapter 3. So after chapter 1, we will move into op-amps, so the beginning of that is something and then we will study more non-ideal effects on op-amps. You've probably studied the very simple ideal effects, and you've derived inverting, non-inverting amplifier rules, and looked at summation circuits probably in 214. So we will review that quickly as well, and as move on to more interesting, I guess, effects, more practical effects of the op-amp. Op-amp is a very important device. It's truly a very remarkable and interesting device, and really it's the workhorse of developing electronic systems, especially for control applications. You raising your hand or?
No.
Okay. So then we will study diodes. So that before we study diodes, we will look at semiconductors and the phenomena of how current flows in semiconductor devices. And then we will study two more very important devices, which are the MOSFET and the bipolar junction transistors, which are the workhorses of electronic circuits, really. So should be interesting, should be fun. The book is interesting. It's the first time I use this book, so I read chapter 1 and 2, and the book is well written. The examples are interesting, so. Should be good to go through it, the learning outcomes, so I'm not going to go through this in detail. The idea is we will study analog electronics mainly, so we will really not study digital electronics as such, even though I will show you a short video of how what we're studying is actually applied in the development of digital electronics, so I'll show some of that. There's a lot of math behind, mainly algebra, I would say, algebra or calculus behind what we're going to be doing. So there's a lot of calculus and frequency domain. Have you studied body plots at all? No? Frequency domain, body plots? Yeah, in 214, I'm sure you studied frequency domain and body plots, right? Transfer functions for simple circuits in 214, right? V output over V input is the transfer function of a circuit, for example, or I output over I input. You've studied that, right? And moving that to S domain. We will refresh. I'm not saying it's, but these are things that we're expected to do. Then we, of course, will have to plot, use body plots to plot these transfer functions, because they will be important for us to understand how op-amps operate. So for us to design a proper op-amp circuits, you have to understand, these the manipulation of signals in the frequency domain, which is a lot of the stuff that you're studying in. Some in 214 and then a lot in 314, I believe. Then we will look at more op-amp circuits, especially with the non-ideal effects, and then we will look at again the transistors that we talked about. And we will be using which spice tool are we using? The simulation. For simulation, we'll use OrCAD Cadence. Okay, so we'll be using OrCAD Cadence for simulation. So when I was a student, it was called Spice, and then PSpice. And Spice is basically the engine, or the mathematical engine. Yeah, it's the mathematical engine behind, many of the circuit simulators is called Spice. And then many of the companies took it and, added a flavor of their own and called it something else, and maybe enhanced some numerical methods to make the calculation faster, easier. I would say Cadence is the biggest company. So they've, I guess, acquired PSpice, and we'll be using their tool. I will use it with you. Again, I don't know how different it is from the old PSpice. It's the same PSpice, so nothing changed. Yeah. So nothing changed since I was a student. So very interesting. Yeah. So, see, I told you this is very established. Yeah. We're so behind. No, but this is the basics. No, this is really the basic. Yeah. So you will use simulation to be able to predict the performance of circuits and analyze the performance of circuits. So we will have a small mini project. I would say, I guess for me, it's similar to a lab. I mean, it's a lab. For me, we will do it during the lab session. It's not, it will have some design parameters so that you can maybe select. I mean, I'm not sure if I should do a mini project or we should do a term paper. I'm not still up for. Do you have a preference? Mini project, term paper is better. I don't know. I mean, again, for me, I'm preparing the course as we move forward. So term paper would include something like, a review of a certain technology, writing a paper about it, or maybe looking at a research paper, a recent research paper, and then writing, summarizing it and maybe presenting. That's one approach. Or another approach would be to do a mini project, build a circuit, and understand how the effect of certain parameters will change the circuit design, for example. Yeah. To build the circuit? You don't want to write? Oh, that's not good. So we'll make her write. So I'll finalize that. I'll work with Wissam and we'll finalize that. Yeah. So we will have 5 lectures, not 4 lectures, at least at the beginning. Okay. So it's. I was initially thinking we should have 4, but anyway. So we'll probably go for 5 and try to finish sooner than later. That's my personal opinion. Yeah. I didn't put Wissam's office hours here. I will get those from him and update the syllabus. So the updated syllabus, later today we will have updated syllabus. So our offices moved. I'm sure you're aware of those. So we moved everybody's in the same place. So mine is 246G, so right in front of the door. So my suggested office hours will be Monday and Tuesday after class. Unless you have the other class. When is 303 class? When is the other class that you're taking? Right at the same time? So maybe I'll shift this. So I'll shift the office hours from 11:30 to 12:30. Okay, so the other class is right after this. So I'll shift the office hours another hour so that I will be available for that, and I'll add Wissam's office hours. As I said, so 2 of these sessions are lab sessions. Which one? They're both Sunday and Tuesday. They changed the schedule, Yes, they changed it. They changed it today. So they're both Sunday and Tuesday. No, this was, I think, Monday before. I think one of them was Monday. Same? Same. Okay. So yeah, anyway, so I would say, so this would be the lab sessions. The 2:15 to 5 would be the lab sessions, and then no, it's 1 to 1:55, and then 2:15 to 5. So the recitation will be, yeah. So we will have. I will suggest this. Okay, my suggestion will be, so we will have 5 chapters. The idea will be 5 exams. 1 exam on every chapter as soon as we finish it, and we don't have a cumulative, and there is no final. That's the. I think it's not a bad way for summer, with how things are gonna be crammed. I think we finish a chapter, take an exam, and that's it. It's done. I like the approach. I don't know if it's something that is, if you're okay with it. I think that's the way we'll go. That's the way we'll go. And we will have the exams in one of these recitation sessions. So every week we'll probably, so not this Sunday, so next Sunday. So I think it's good to have it on Sunday, so you have the weekend before to study. So I would say that every Sunday, unfortunately, we will have an exam. I think that because it's 6 weeks, we don't have one this Sunday. خلاص, but we will have the week before, right? So, like for example, this Tuesday, we should do the recitations that are important for the Sunday's exam. It's a killer. For me and you, believe me, it's like, doing this. I think it's very fast, a very fast pace. But again, just enjoy it. Enjoy the material and the time, and you will move forward. It'll be fine, inshallah. So that's the suggested plan. The book is Sedra and Smith's 6th edition textbook. I'm sure you've received that already. That will be the main reference. So as I said, there will be 5 exams on each of the chapters. I think I put 60% on all the exams. So how I divide them up is 10 and then حتى. So yeah. So 12 points on each. So and then you just get done with that chapter. It's because the material is pretty independent actually. The material is pretty independent, yeah, which is better. And then we don't have an exam on the finals during the final session. So I think it's too much. I think this way is good for the students, yeah. So it's like having a quiz. It's like having a big quiz every week, and that's it. As I said, the homework assignments will not be graded. So you will submit them and you'll get a grade. You'll get, yes, the person submitted their homework, and that's it for each week. And then there's no, okay, you cannot get, there's no grade for it, okay? So you submit the homework that it looks legitimate, Wissam will give you the full credit. You submit the homework and it's a half-baked thing, then Wissam will give you half the credit. But we're not going to give 10%, 20%. It looks like you've done your job, because you will have a quiz on it already, right? So it doesn't make sense to. Yeah. After, that's why, but that's why I will not, unless it's an excused absence, blah, blah, then you can submit the homework late and maybe get partial credit. But for me, since it's not graded anyway, you submit it and that's it. Yeah, it's you submit it, you get the credit for it, and you move forward. Then we have to post, because we cannot delay posting the solutions, right? So we have to post the solutions right away because of the way that the semester is moving. Again, the exams will be after. We will agree. For example, let's say we don't finish the material, it's not going to be Sunday. But maybe we'll do it in the Tuesday session, like Wissam suggested, right? But I will notify you, of course, right, in advance. But I will try my best to make it that way. That every week we have an exam, either Sunday or Tuesday. That plan it that way, and then it will depend on how we are progressing. Okay.
So we have
10 or 12 days, yeah. Sunday or Tuesday. Sunday or Tuesday we'll have, depending on how the classes go. Yeah, you can go home and tell your parents, I have a midterm next week. Yeah, so what can I do, right? It's 6 weeks. 6 weeks. It's anyway, so that's homework, the grading. So the quizzes that we will have, the quizzes on the homework will be about 10%. And these will be during the recitation session or one of the lab sessions, depending on Wissam, what Wissam thinks, how his schedule for the lab is going. If he wants to do it during the lab, he will do it during the lab. If he wants to do it during the recitation session, he will do it in the recitation session. That's handled by Wissam, the quizzes here. I don't think we will have quizzes in the class. There may be occasional, short quiz here and there, but I'm not sure if we will. There may be occasional ones. Homework submission, as I said, so it's 5% just for submitting the homework on time, legitimate, work effort done on it. Yeah. it's for your benefit, guys, right? You do the homework yourself. Even if it's wrong, it's okay. But try working on it. That's for you. The mini project or the paper will have 5%. I will make a decision on that. I will speak to Sam and we'll decide. And then the lab 20%, and the exams will be 60% of the grade. So this is sort of how we will chop it up. Yeah. I think Wissam is saying that we have 8, not 7 labs, right? So which one am I missing? Yeah, but that's it. Op amps 1 and 2. Okay, I will update this with with feedback from Wissam. It's 7 or 8 labs and either a mini project or the term paper. So class attendance, again, I don't like to push, and you're adults, I don't like to push, but I don't want to come and don't have, there's no students in class because I'm recording, right? So I would not appreciate it. I mean, I'm doing, I'm taking the time to do the recording and post it online, etc., etc. So, at least it's good to have some interaction in the class. For me, the recording is for people who, fine, they really missed the class and, for a reason that, fine, they have a, it doesn't have to be a real excuse, big absence. I mean, according to university rules, yes, you need to be in class, blah, 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 etc., etc., right? You're adults. I don't deal with you with rules A, B, and C unless you deal with me with rules A, B, and C, right? So, but, the way I would like to make sure, we're here to learn, and I don't take attendance, etc., etc., but if I'm pushed to do that, I'm pushed to do that, right? So if I come and I cannot start, because if I come and people are not here on time, then I cannot start on time, then that will delay me, then it will delay me not being able to finish the material. Then at the end of the semester, there are certain outcomes we're supposed to meet, and then you say, oh, we didn't meet the outcomes. We didn't meet the outcomes because you come, if people are coming late or not coming to class, it's difficult for me to teach it, right? So let's make sure, fine, it's a short summer, let's get it over with, come to class, don't spend extra time, watching the videos for no reason. You watch the videos if you need to review a certain section, or if you missed something, or fine, you had a situation and you had to miss the class, stuff like that is okay. You're adults. I'm not going to talk about, all of this disruption and AGI honor code. Again, you're aware of the AGI honor code. We're expected to all meet it and comply. And again, you're here to learn. You're not here to ruin your future. So let's make sure we learn and we do it properly and follow ethics that we all know exist and we all know we should follow, right? Phones, etc. Just turn them off before you come to class, please. So that's really the syllabus. I'm not gonna go through the rest of the stuff here. So this is the syllabus. It's on the website for your reference. The lecture and lab schedule is also on the website. This was prepared by Wissam. So we may have some occasional changes here and there, but generally we will have chapter a week, or that's sort of chapter every week plus. That's sort of the plan, right? So we have 6 weeks, we have 5 chapters. Every week plus 1 day or so, we will be covering the chapter for material. So there will be an introduction lab. Sorry, this week I did not pay attention to that. There will be an introduction lab, just the introduction to the lab this week. So please do that, and then there will be a recitation as well on Tuesday. So Tuesday,
We have a recitation.
yeah, because the exam is next week.
So we have like an exam
And the schedule, which schedule? This one? Yeah, no. Again, I will update it. As I said, it was something I wasn't sure. I was getting their feedback, whether we have, 3 exams and make, one in the finals week, or my preference is just one every chapter and get it over with. That's my preference. Short 1 hour exams, like the recitation sessions are what, from 1 to 1:55? So 55-minute exams and get it over with. 1 55-minute exam in every chapter, and that's it. Yeah. That's my personal preference. Yeah. So I will update this to reflect that. Yeah. So, but as you see, there's really no time. Every week there's labs.
بس like can we have suggested problems and the book looks scary يعني.
The book looks scary. Yeah, I know my wife. When I showed it to my wife, and I was like, I have to teach this. Well, she got scared too, but she's already scared. Lulu was scared.
All the subjects.
Okay. So we'll figure it out. Maybe what we can do is, maybe make photocopies of chapter by chapter. Yeah, we're only covering 5 chapters, so it's actually only until
Yeah, but each chapter may have multiple problems. Like we
Wow.
have to do it in
it's big. No, we're covering a good chunk of the textbook here. Yeah, again, the homework problems will be indicative of what you should be doing, right? You want additional problems? There's lots of. Yeah, for the practice, the textbook has a lot that we can. For example, we look at the homework problems. If they're not enough, we can assign some more, for reference here. So we can. But the textbook is really a good textbook. It's not a bad textbook. So this is the plan. Again, I will update it as we move along. I will update it, with the plan that we talked about. The idea of having the 5 exams to cover the material. With that being said, we'll move forward. I don't have a watch, so I'm looking at the time here. So we'll get started. I think if you have any, we'll get started with the material since we have to move forward. Unless you have any questions, we're okay. We're good. So I have some 2 interesting videos. Since you haven't played with microelectronics, seriously before, your main interaction was basically 214, 215. So there are some nice, lots of nice videos on microelectronics technology available. So this is just one interesting one that, because it will allude to something I will talk about next. Yeah. So this is an example of a microchip. So the course covers microelectronics, right? So, and what we mean there is, we're actually studying analog. This electronics is something that we can use in analog circuits, or we can utilize in digital circuits. So these are sort of the 2 main families, and we can be doing this in a discrete fashion. Discrete meaning a circuit that you will see on a printed circuit board, for example, will have some discrete transistors, capacitors, etc. So that's sort of called a discrete circuit. Or you can have what is called a microelectronic circuit, which is a integrated chip or integrated circuit that this video is zooming into right now. And inside this chip is, are lots of, sort of transistors, capacitors, inductors, they can put them, etc., etc. So inside this chip is a lot of the stuff that you can also apply in discrete form outside, right? Why am I showing this? Because when we talk about the semiconductor part, it will become a bit confusing. What's inside this thing, and how are they making it, and how does it really work? And I have another interesting video on how they construct these devices. And there's lots of stuff online, but I want to show you, let's zoom into this and then look at a simplified video of how, for example, you make a simple AND gate or a simple OR gate on a semiconductor. And this, when we refer to microelectronics, it's called microelectronics because originally the form factors were in microscale. So the distances between objects and the distances between objects and materials here on this chip were in the range of micrometers, right? Today's technology, we are in the range of nanometers, right? So we are shrinking this smaller and smaller and smaller. We're able to construct smaller and smaller devices. But at the end of the day, if you look here, this is what? It looks like, like a 3D construction project, right? So it's a, silicon wafer, and you would put different layers of materials, and then you would remove certain, have you seen a circuit board, printed circuit board? I will bring a printed circuit board with me next time. But what is a printed circuit? Printed circuit board is a base material, for example, and then you would have copper on one side, and what you would do, for example, is maybe draw the tracks or draw using a certain material on places where you want to remove or etch out of the material. and then you etch it using either mechanical means, optical means, chemical means, and you will remove material that you are not interested in. And you will leave what? You will leave the interconnections between the circuits that you are interested in, right? So that's,
Everything will be on the block and we just like take from the block.
yeah.
So,
So
it's the
you,
opposite.
so the board, no, it's not, it's the same as here. So it's a board that has a layer of copper, right? This layer of copper, you will, for example, draw your circuit on it. Your circuit, you want to keep it, because that's your circuit that you want to keep on the board, right? And then everything else you want to remove. So you want to remove that. So you will etch, and it's called, you will etch that off the board. You will etch it either mechanically, maybe we'll visit, I'm sure you will visit the electronics shop at some point in your, do they visit it at all in 325? Or, I think, yeah, I think it's good to visit the electronics shop and look at the PCB etching machine. It removes the material that you do not want and leave the circuit material that you are interested in on the circuit, yeah. And you can have, and here I just talked about a single layer, right? But typically today's electronics is maybe multiple layers. So you will have a layer of this substrate material, a layer of copper, a layer of the substrate material, a layer of copper, a layer of substrate material, layer of copper. And you would be constructing the different layers. So on every layer you'll be drawing your circuit. Every layer you're drawing, and then removing parts that you don't need. You're drawing a circuit, removing parts that you don't. That's on the, that's from a printed circuit board perspective. Microelectronics is constructed in a very similar fashion. So we start off with the silicon, we start with sand, it's processed to create pure silicon. This silicon is sold to these fabrication facilities in the form of big chunks of material. They chop those up into very thin wafers. And these wafers are where you start building your circuits on, right? So, and they're built layer by layer, and we saw how this looks like a simple construction project, right? So, and each of these interconnections, etc., were built layer by layer. The technology behind building it, etc., we will not be covering that in the course, but I found another, short video that now that we've seen that they're made by
See how
layers by
computers
layers,
add numbers
I thought this
in
was
one lesson.
interesting.
Inside a computer, you'll find a motherboard. The motherboard
This is
acts
not
like a
interesting.
chassis inside a car, giving all the components something to connect to. On the motherboard is the microprocessor. Most microprocessors have some jagged metal on top called a heatsink to prevent overheating. If you remove the microprocessor and look underneath, you'll see a lot of wires sticking out that connect from the holes in the motherboard to the main part of the microprocessor. The microprocessor is made up of different areas that do different things, such as adding or storing numbers. These areas are mostly made up of one thing, though, the transistor. Here is a 3D view of one. The transistor's base is a semiconductor, which sometimes conducts electricity and sometimes does not. The semiconductor has positively charged areas and negatively charged areas. Electricity will not flow between the two yellow areas unless a conducting channel is opened up in the green area. A conducting channel is opened up in the semiconductor when a conductor, such as metal, is placed above the gap, wrapped in an insulator like glass.
So see, this is the construction project, right? So we have a semiconductor material. In semiconductors are materials that can act as an insulator, and they can act as a conductor, right? In a controlled fashion. That's the beauty behind the semiconductor. So here is where this construction project is happening, right? Again, we don't show the details of the construction project, but they tell you, okay, so you have these two areas here that you want to conduct current between them. You cannot conduct current between them unless you have to have a closed loop, right? Any current will flow only in a closed loop, right? So how are they constructing the closed loop? By adding metal material here with some semiconducting material inside it as well.
And electrified. For electricity to flow through the conducting channel between the yellow areas, there must be a source and a drain. In other words, an input and an output.
Right, so it's a fancy words for input and output. It's nothing but a terminal coming in and a terminal coming out. And they are just all additional conducting materials, all part of this big construction project that you're building.
They're both made from conductors as well, like metal.
Just
If
a piece
the
of metal.
input is charged, it cannot flow to the output unless the gate, which is the piece of metal in the middle, is also charged. When the gate is charged, it opens up the conducting channel in the semiconductor, allowing electricity to flow down through the source, over to the other side of the semiconductor, and back up out the drain.
Right? So the transistor is nothing but just a path for current to flow in a controlled fashion. That's really it, and it's constructed using nothing but either semiconducting materials or conducting materials. Right? Like the drain and the source are pieces of metal, and the rest is semiconducting material. And this semiconducting material, we will look at semiconducting material, and they said that it has some p-type and positive and negative type of material. Right? We know that current likes to flow from positive to negative, right? But they're telling us that it will not flow unless you apply a gate current or a gate signal, where you apply it here. Why are you doing that? Because only when there's an electric field will current flow in a semiconducting. Its properties will change when there's an electric field, that electric field applied on top of the material, right? So you have this semiconducting material wrapped around the conducting material that is on top of another semiconducting material that is doped in a certain way. We will talk about what doping is, of doping of semiconductor materials to make it positive type or negative type of semiconducting material. And you build this construction project, right? And that's, this simple construction project. When you zoomed into this microprocessor, you just saw these things on top of each other, right? These things on top of each other are nothing but layers of semiconducting material, some conducting elements, semiconducting material, some conducting elements placed in a certain way. The basic building block is this transistor.
What do you mean? Like made of transistors?
Yeah, it's full of transistors. Why is it full of transistors? We will look at that when we build a circuit, right? Especially MOSFET, especially digital circuits are mainly MOSFET-based circuits, and we will look at that in the later chapters. Yeah, but op-amps, for example, they're full of these transistors as well. A lot of them are BJT-based devices. So we will study both BJT and MOSFETs to look at which devices are used more on the analog side and more on the digital side. But the basic building block is,
The neat thing about this setup is that there are no moving parts, and you are using electricity alone to turn.
Right. So the idea of no moving parts is very interesting because if you go talk to mechanical people, mechanical guys, when they want to turn on a motor, what do? Put a relay, right, or a switch, right? So here we are able to do this electronically, right? So, and we can do this at very low current levels, or in 438 we study how this is done at very high current levels, also with semiconducting materials, right? With similar devices also, BJTs and MOSFETs, but they're adapted for power or high power applications. So power BJTs and power MOSFETs are what we use. There, the structure is very, very similar to what we're going to study. It's just the way we use them is different. So because the way we're using them is different, the scientists and the device guys design them or manufacture them a bit differently so that they can withstand higher voltages and currents. But the basic idea is very similar. Yeah.
On and off other electricity. The breakthrough idea with this technology was using it to form logic gates. For instance, if you have two transistors and you add power to the inputs of each transistor and then add switches to each of the gates and allow the outputs to both flow directly to a light bulb, you have created an OR gate, which has this symbol. Turn the left switch on, or the right switch on, or even both switches on, and the light bulb turns on. If you change the wiring so that the output wire of the first transistor runs to the input wire of the second transistor, then you've created an AND gate, which has this symbol. With an AND gate, if you only turn the left switch on, then the light bulb is not on because the electricity coming from the first transistor is stopped at the second transistor. If you only turn the right switch on, the light bulb is not on because there is no electricity flowing through the first transistor to reach the input of the second transistor, so the light bulb does not turn on. Both switches must be on in an AND gate for the output to be on as well. On and off can be represented in the case of the switches as 0 off and 1 on.
You can continue this video. I thought the first part was very interesting because, after looking at the zoomed in of the microelectronic circuit and seeing all these things on top of each other, you know, this is more of a cartoon sort of representation of this, and it shows you something that you know. Okay, so an AND gate and an OR gate. So basically, yes, these, you know, if you've taken 350, you've taken 350, no. So you've taken 350. You've played with the FPGA, right? The FPGA, you're programming it, right? But you're programming fine. This is a very high level communication that you have with the FPGA. What's inside the FPGA is nothing but a bunch of gates. It's all gates, ands, ors, basically nands, nors. That's exactly what's inside the FPGA. It's only gates. And this code that you're writing has an interpreter behind it that is going to translate the code that you're writing into gates, into a connection of the circuits inside an FPGA. So that's the beauty of FPGAs is, you know, it's like a configurable sort of, you know,
Don't you use matrices in this?
matrices. What do you mean by matrices?
Matrices. In program. Matrices.
Yeah, when you program matrices, again, there's you're programming something in a very high level language, C, for example, right? There's an interpreter that is converting what you are writing in a very high level language to something that the FPGA will understand. So when you program the FPGA, it is connecting the gates in a certain way. So here they connected, and these gates, when they are actually nothing but transistors. So at the end of the day, you are basically reconfiguring the way that the connections of the transistors are happening inside the FPGA chip. Yeah. So that's what you're doing in there. Yeah. But I thought this was it's a simple video, but it gives you a good idea of, or relates the two videos we saw. So we'll start with I don't have a watch, that's why I'm looking. Okay, so 10. So we'll start with the first chapter. Material, again, these are the notes prepared by Dr. Bina. I've started preparing slides, but I worked from the back, right? I started preparing from chapter 5 and chapter 4 and chapter 3 and chapter 2. So chapter 1, I may refresh, I will use this material now, and Dr. Bina did a very nice job, extracting the main information from the chapter. But I may convert this to slide format as we move forward. Yeah. Again, so initially there's basically we talked about microelectronics and the relationship between the 214 course and the 325 course, basically the basic circuit analysis versus more in-depth electronics analysis, and then the basic op-amp as a block versus how do you actually construct a simple amplifier circuit. And really the core is the development of amplifiers. The core theme that we're going to be looking at is how amplifiers are designed and analyzed. Yeah. So we talked about the basic requirements from 214 that we should be interested in or knowing, and this is something that is expected from you. So mostly what we're doing in electronics is, again, taking signals from physical phenomena, and then converting these signals from physical phenomena that are in the analog domain. So the light intensity here, how would you measure light intensity in this room? You would have a sensor that measures light intensity. That is not what we're studying in this course. So the sensor, the specific sensor that does that. For example, temperature in this room. One thing that you know is that can act as a temperature sensor is a simple resistor, right? So the resistor changes its value with temperature, right? So that happens to be a sensor in that case. But the sensor by itself will not work. You will have to connect a circuit around it. And then what do you do after that? When you connect, you have a sensor connected to a circuit to understand that signal. Sometimes that sensor is not able to provide power, right? So sometimes sensors are going to be some devices that measure the physical phenomena. So they measure the light intensity, they measure the temperature, they measure the pressure, etc., etc. And they provide a voltage or a current signal. So some sensors, for example, if it's a sensor based on changing the amount of charge on a capacitor. What is changing charge on a capacitor going to result into? Current, right? If charge is changing on a capacitor, then the result is current, right? So some sensors, you would model them as, a current source. Some sensors, you would model them as a voltage source. And we know that you can, convert, the Norton equivalent circuit and Thevenin equivalent circuits to each other, right? So you can actually take something that is modeled as a current source and move it into something that is modeled as a voltage source to simplify your analysis. That's what you did in 214. So we will do stuff like that here. So we will start with the sensors, the source, and these sources will be producing voltages and currents. These voltages and currents we would like to analyze or add up or do something with them. But these sensors happen to be devices that, for example, this capacitive type sensor that produces a change in charge, meaning a change in current. This device is a small capacitance, for example. It will not have a huge amount of current that you can utilize to, for example, run a motor. Let's say you want whenever the sun is up to turn on the AC, right? You're not going to use the sensor to, the sensor that is, okay, I detect sun somehow by and then the current flows, for example, when I detect sun. This current that's flowing from the sensor is not something that you can utilize to go and run a motor, for example, right? So you want to interface, put something in the middle that will, understand that there's sun outside by, you measured some physical phenomena, and then do some processing of that circuit, amplify that circuit, and then deliver a current signal to the motor to turn on. So, and that's the part that we're studying. That's our main interest. How do you take that signal and then pre-amplify it? Maybe you want to change its voltage level, maybe. Or maybe the voltage level is okay and you just want to change its current level, right? You want, for example, the signal is producing, somehow the sensor is producing enough voltage for a small DC motor. So the voltage is fine, you're happy with the voltage. But the current is not enough. So you would put in a power amplifier, not a voltage amplifier in that case, right? So we will study the design of these voltage and power amplifiers and their characteristics.
Like, does it depend on the amount of the thing I'm getting? Or
Now, typically, all sensors will be devices that will not be able to supply enough power. They will be measuring a physical phenomenon. For example, there's a lot of people working on biophysical sensors and stuff like that, right? So you're measuring heartbeats, or it's a very low signal that you're measuring. So, or you're measuring blood flow, or something like that, right? These devices are going to be, they're measuring these physical phenomena by, for example, let's say, people are looking at micro electromechanical systems now. Let's say you have a small water wheel that you made in a MEMS device. MEMS is called micro electromechanical. So you made this water wheel. This water wheel, you created a micro generator connected to that water wheel that will create a voltage when that water wheel moves in response to current flowing in, blood flowing in the person's veins or something. I'm not a sensors guy, right? But that's, people are working a lot on micro sensors and MEMS-based sensors for applications in medicine. So we take after that. Okay, they developed a sensor. Now I want to take the sensor information. Okay, when I detect that the current flow rate or the blood flow rate is changing rapidly for no reason, then I'm going to detect some medical condition that I want to look at, right? So when the blood flow is constant but low, I have another medical condition. When the blood flow is constant but high, I have another medical condition, right? So I take all of these, so all of this is interpreted for me. I'm looking at, at the end of the day, guys, I'm not very interested. I am interested, but I don't care from this perspective of this course how this sensor is made. But I care, at the end, this sensor looks like a voltage source with a resistor in series. That's the Thevenin equivalent. Anything in the world, remember, any circuit, you can apply Thevenin equivalent or Norton equivalent. Right? So any circuit, everything to the left here, I can take and at the end of the day, for me, you look like a voltage source with a resistor in series. The importance is this voltage source. Is it AC or DC? If it's AC, does it have multiple frequency content or just a single frequency content? If it's DC, what's the value of the DC voltage? The resistor in series, is it big or is it small? Which one do we want? We will look at that, right? So this is the main issue, main consideration we're going to look at in this chapter. And then this Thevenin equivalent circuit, I'm going to hook it up to my circuit. My circuit may be an op-amp. I have a model for the op-amp. This model for the op-amp may have some time-dependent components, like a capacitor, right? I mean, anytime you have, remember these chips, We're what? They're just layers of, semiconductors, conductors, semiconductors, conductors. So even if you're not constructing a capacitor by intention, there is parasitic capacitance. There is, anytime you have two plates or two nodes that are oppositely charged and a dielectric between them, what is that? It's a capacitor, right? So inherently you will have in your models for op-amps, for example, in your models for transistors, you will have some capacitances and maybe some inductances as well, right? So then we are hooking up our Thevenin equivalent circuit, which is a source and a resistor, to another circuit that may or may not have some capacitive or time domain or time dependent elements, and we're hooking them up to each other. How do we want this circuit to behave, this op-amp representation? Do we want to measure the voltage and current coming out of that sensor, or do we want to measure even a smaller value of that current and voltage coming out of the sensor? We would love to be able to measure, if you have a sensor, you would like to be able to measure the voltage exactly that's coming out of the sensor. You don't want your circuit to affect that measurement, right? Otherwise, if your circuit is affecting the measurement, then your circuit is useless, right? You would like to create a circuit that does not affect the measurement poorly. And at the same time, so because if you don't affect the measurement poorly, then you can process it and extract the right information. If you've affected the measurement, then you're not going to extract the right information. Garbage in is garbage out, right? That's simulation. Simulations are nice. You come up and your PhD student comes and he has great results from his simulations, right? But then he builds a circuit and everything is messed up, right? It's because simulations is as good as the inputs that you created, right? So you created something and then you put some nice inputs. Add these nice inputs, wow, the results are excellent. And then you build it and it burns up, right? So it's because you did not simulate the right process here. So we're going to start with an analog signal. And then this analog signal, as I said, we will typically have, some physical phenomena. This analog, and that will be measured using a sensor or a transducer. And then we are interested in this part. That's what we are interested in this course, right? And then we hand over the signal after we've processed it to something more digital, 350 type. So we converted it to ones and zeros, and then we give it to the 350 guys, right? So we are more interested in this block in this class. So I think time is up, right? And so we have 2 more minutes. So we start with, again, we will start, and some of these sensors will give you a signal that has some DC component, or some signal that has some AC and DC component together. So it depends on the physics of the sensor, right? So if it's a sensor that provides an output that has a DC offset, for example, this analog signal here is an indication of temperature outside, for example, and it is shifted from DC. Typically, the sensor manufacturer will tell you it's because of the physics of the sensor, how the sensor was made. It's giving this DC offset. You, as an electronics designer, know that the data is not in the DC offset, right? Based on the data sheet, for example. The data, for example, is in the AC signal by itself. So what do? You now have a signal that has some AC content and DC content. So how do you extract the proper AC content from that? How would you extract AC content from a signal that has both AC and DC? You have a signal with AC and DC content like this, right? This is AC and DC means, as long as the area on top does not equal the area on the bottom, that means you don't just have a DC signal, right? The average value, if there is some average value to the signal, that means it has some DC content. If any time that the signal has a DC, some average value, that means there is some DC content here. But this data sheet, for example, tells you explicitly the sensor produces a signal corresponding to the physical phenomena that is shifted by a certain DC component. You want to process the signal, so you have to filter out the DC component, right? So you need to filter that out or subtract it. If you know exactly what that DC component is, subtract it, for example, from the signal. So you've taken circuits that subtract different inputs. In op-amp circuits, you've taken summers and adders and subtractors and integrators and differentiators, right? So, for example, in a case like this, you would need to subtract the DC offset Subtract the DC offset, you're going to be left with only the AC signal. That is going to be containing the physical phenomena that you want to measure. Okay, this AC signal is small. What do? You want to amplify it. Maybe you want to amplify the magnitude. So you have a voltage amplifier. Or maybe the voltage magnitude is fine. Fine for who? Fine for the processor after that. Remember, we're sending this to a signal processor or a microprocessor after that, right? So the processor will have an ADC, an analog to digital converter. This analog to digital converter will have an input range. This input range is, let's say, some analog digital converters will only read positive, so 0 to 3 volts, for example. So if it's 0 to 3 volts, what does that mean? That means if my signal had a DC offset originally of a half volt, and I subtracted that, so I brought everything down to an AC signal, then my ADC is actually only measuring 0 to 3 volts. So what is the DC bias? I need to add to my signal again, so that at 0 to 3 is my full scale for my input for the ADC. So 1.5 is the 0 for the ADC. So I actually have to take my signal, shift it by half, remove the half, subtract half DC offset, because that's what the sensor was giving me. And then I want to pass it to my signal processor, but my signal processor ADC input is 0 to 3 volts. So I need to take that signal, shift it by a DC offset of 1.5 volts, so that 1.5 volts is my base, so that I'm covering the full range of the ADC input with my signal. And then, let's say my signal was, 0 to 3 volts is my input for the processor, but my signal was in, plus minus 20 microvolts. I take that plus minus 20 microvolt, and I can send it to the processor's ADC input. But that's useless because I'm not utilizing the full spectrum or full input of the ADC, which is 0 to 3 volts. So I have to do what? I have to amplify the voltage of that signal, right? So I have to use a voltage amplifier. Fine, we use the voltage amplifier. Then you look at, you connect the two, and as soon as you connect the two, your sensor signal changes, collapses. It was plus minus 20 microvolt, and it collapsed to 1 microvolt, plus minus 1 microvolt. What does this mean? It means that when I connected the two circuits together, something happened. So they are not compatible somehow. Why are they not compatible? This is something that we can easily represent using a simple circuit like this. For example, if I have a sensor that is providing a certain output, so my sensor is represented using this Thevenin equivalent circuit, and this is my representation for my processor. For example, we will see why this can be a representation for a processor. So this is the input voltage for the processor, right? What is this input voltage equal to? Our processor, our sensor. What is this input voltage equal to? Simply speaking, it's Vs, Kirchhoff voltage law, right? Vs multiplied by our processor over our processor plus Rs, right? So what would I like the input voltage to be? I would like the input voltage to be equal to the sensor voltage. That's what I would like to be. So if I would like it to be that way, what does this mean for this? It means that I would like this Rs, Rs to be a lot smaller than Rp, or ideally I would like it to be 0. Yeah, in order to get 1, because I want to measure my signal. I want my processor to see my signal. So I would like this Rs and Rp to be related in a certain way, right? And they were not. If I hooked them up and then I saw that V input is much smaller than Vs, I collapse the signal. What does this mean? It's because my condition here was not satisfied, right? So connecting the processor to your sensor ruined the signal. So what do? You have to put something in the middle. You have to put an amplifier block in the middle. And you do not want a voltage amplifier in this case because you actually want the same voltage. You want a power amplifier. You want something that will be able to push current here in this branch without affecting the current in this branch. Ideally, you want the current in this branch to be 0, because I would like to measure this. Because if I have current in this branch, there's a voltage drop across this resistor. Then I'm not measuring Vs anymore. I'm measuring Vs minus the voltage drop across this resistor. So ideally, I want this current in this loop to be as small as possible. right? So that I'm not affected by RS. And I'm measuring VS here or something very, very close to VS. That's what I would like to see from the sensor. And then I would like to take this VS that has no power, not able to push any current through this branch, and then put an amplifier stage that is going to amplify the current. It's going to amplify the current and be able to push enough current in this stage, regardless of this value of resistor, so that V input is equal to Vs. Right? That's the story we want to. Our work will be this block. This is our work.
So we would be given the conditions.
Yes, we will be given circuit conditions, input and output conditions, and we will see how to design this block. Mainly, this is a lot of the stuff we will do is on this. Okay? So we will stop here because past the time, and we'll continue next time tomorrow. Every day I see you.